hosting today's webinar. With me today is Amir Sadiq. He'll talk a bit about himself a little bit later here, but let's just begin by going over some housekeeping stuff. If you would like to turn off notifications for this session, here are the steps on how to do it. Also, if you have any questions during the session, please use the Q&A box right here in order to ask any questions. We will have a Q&A at the end of the session. We expect this to run about an hour with about 10 minutes at the end to answer any questions for you. I'm going to leave this on for just a second. Amir, if you haven't already turned off your sound and settings, if you don't have a headset, please do that now. That way we won't hear the sounds as they come in while you're presenting today.
I don't have the headset with me today.
Okay, great.
Yeah,
So yeah, if you'll follow the instructions just to make sure that those sounds are off, then we can ensure that we don't hear anything as you're talking. We do still have people coming in, which is wonderful. Welcome, everyone. All right, I'm just going to answer a couple of, do you need me to go back?
Is it better now? Is there any background sound coming?
No, I'm not hearing anything from you.
Oh, okay.
Are you hearing the sounds on your side?
Yes. I still hear the notification. Can you please get back to the slide? Like this.
Sure. Yep, absolutely. No problem. Thank you, everyone, for bearing with us for a minute. Anyone else wants to turn off their sound so they don't hear messages coming in and so on, these are the steps to do so. Okay. We do have a couple of commonly asked questions throughout the webinar, so I'm just going to share that information with you. Everybody will get a copy of the slides and the video recording that does occur fairly quickly after the end of the webinar. If you haven't received anything to your email within 2 business days, please reach out and we'll make sure that you get those. In addition, a certificate of attendance is awarded to everyone who attends the live session. We will be providing the link to that at the end of the session. So you do have to attend the entire session. You don't have to stay for the Q&A, but I will be putting up a link at the end, a QR code for you to scan, and also a link I'll copy into the chat so that you'll have multiple options to access that.
Okay.
So let's just talk a little bit about who we are. EIT is the Engineering Institute of Technology. We are a dedicated engineering institution. We offer courses that are taught by engineering specialists like Amir here today, people who work in the field who are knowledgeable and have industry experience. So when they teach you, they're talking about things that they've actually had hands-on experience doing. All of our programs are industry oriented, so it's going to be engineering specific or engineering adjacent, such like project management. And then our delivery is available online for all of our programs and on campus for our higher education programs. We do have 3 campuses, one in Perth, one in Brisbane, and one in Melbourne, and we offer our different programs there. However, all non-higher ed, so all of our vet programs, our certificate programs, and our diplomas are only available online, but we have been doing this for a long time, and we have a great online delivery system, online and virtual labs, virtual and remote labs. We offer software access for courses that do require software. Sorry, I'm stumbling a little bit, but civil and structural is one of those that you'll get a lot of software access in the courses. That's all included in the price of our programs. If you have any questions about any of the courses, I will drop my email into the chat here in just a little bit once Amir gets started so that you can reach out to me um, and ask any course specific questions. You can ask them in Q&A, but also you'll have my email address. So I'm going to turn this over to Amir, who's going to talk about the stabilization of expansive soils by using eco-friendly enzyme-based materials.
Thank you, Maria, and hello, everyone. Thank you very much for attending today's webinar. It's my pleasure to share my knowledge with you all. So I have obtained my bachelor and master's and my PhD at Aromat University from starting from studying 2009 and completing the whole education journey from 2021. Then I work on the I've done some more teaching in different areas, transport engineering, concrete structures, steel structures, and further. Then I also have worked in the industry for about 2 years as a geotechnical engineer. In general, I was working as a geotechnical engineer, but I was given mainly in the pavement design area. Also, at the moment, I'm working at Automatic University as part of the food green development at Automatic University, and at the same time, I'm also teaching at the IT University as a lecturer. So this is a quick background of my expertise. I've done geotechnical, digital twin, digitalization, and concrete structures, concrete material, a bit of circular economy. So as an umbrella of different aspects of the civil engineering applications. Today, we're basically discussing about the what are actually expensive soil, what do you mean by expensive soil, then the soil stabilization itself in general, and use of the enzyme material, or there's sometimes it's called enzymatic soils at the laboratory scale, and then its transition to the field actual applications here in Melbourne. So when you're talking about the expensive soil, what are actually expensive soils? We're basically typically talking about the clay. It's the clay that is the major issue here. Because clay, when you're talking about the aggregates or sand or silt, they're all part of the soil, but when it comes to the clay, it's actually making the major issue. Now, clay itself is basically some kind of mineralogy material, compounded, chemical compounded. So starting from some of these silica sheet or aluminum sheet bonded together, but then it depending on their binding, which affects the actual clay. So the colonite, basically, these particular sheets are have a quite high adhesion use of the hydrogen bonds. So they're not much considered as the expansive clay material. So we are not worried in that area. But when it comes to the alite, it's slightly because of this electronegativity construction, which at this time also get some of these positive involved to bind these clay particles. It's mainly the montmorillonite, so that is actually the main one because there's not much bonding occurring between these chemical layers, where water actually can get into between these different layers and actually making this issue of expansive. So when we're talking about expansive, we're really talking about this swelling and shrinkage. Oh, it's a swelling that's the main problem. If there is no swelling, then there is no shrinkage. So the water is actually leading this expansive or this swelling to occur. which during the wet season and then during the dry season, the water basically evaporates or releases from these particular molecules. Then that's where the shrinkage is happening. Now, my next few slides actually is going to be further discussing about that. So this is the a schematic diagram that represents the swelling behavior. So considering we have these different layers or different molecules of the clay, and they are at the origin state at this time, at this stage, but when there's with the addition of water, so what happens? These particular particles of the clay kind of gets away from each other because in between them, they get filled with water. Now, if we also check the void shape, in this case, basically it's irregular, but during the wetting program, this void actually becomes spherical or semi-spherical. So they don't have this particular irregular shape anymore because the reason for this void is basically the equilibrium forces or circumferential forces leading this pore or these air pores to have these particular spherical or semi-spherical shapes. So this is the swelling. So you can see the particles are actually getting away from each other and there's water involved. Now, considering the same mass of the soil, when it's drying, so what's happening in that case, these particles will get close to each other. However, they will not get to their origin as they were initially. So they will still be a bit away from each other, but not as much during the wetting. Then all of that space that's actually there, it will lead to have crack development or the large voids. So this actually is the shrinkage issue. So when all the particles get together, then there is not the available space is actually there's no particles, there's no water, so they become the air void, or this air void becomes the surface crack, or even deep crack, wide crack. So depending on the nature of this crack and depending on shrinkage. So this is a very initiative or preliminary approach of why we have this expansive clay. What is actually expansive clay? Because in geotechnical, we don't really go through this much details. But if we go through the having a better knowledge, what is actually clay, why is this expensive, then we need to know this mechanism. So when we took in general, the behavior of these clays, expansion and the swelling and the shrinkage, what actually does to this structure. So considering this particular structure we have, we can see during the swelling, there could be because it's swelling, so this is a volume variation. What's happening is actually is going to uplift the structure. Of course, during the drying, this structure will be downlifted or moving downward because of the cracks happening and because of the behavior of the soil. Now, at this stage, it does not really mean if we have the swelling occurring, basically we will have the structure moving upward. The swelling is occurring, however, the structure is actually sinking because of the strength is reducing. And in that case, we have cracks happening. However, during the initial stages of this swelling, we get the cracks happening, and the cracks are actually going through the corners from the center upward to the corners. During the shrinkage or the drying, because the structure is actually sinking, there are two different opposite mechanisms. So the crack will start from the center of the roof all the way to the corners or to the sides of the ground area of the building. So we need also to understand when you have a look at the structure, the shape of the cracks, where the cracks are actually, the direction of the crack, it quickly gives us a hint. What are these particular mechanisms? Is it a swelling or is it the shrinkage? So depending on different application, there might be some shrinkage because the swelling has happened in another site, maybe a few hundred meters away, but the shrinkage is happening at the stage here. So then we have So then when you're considering that kind of swelling or this expansive soil issues, now in Victoria itself, it's well known the soil behavior is not that good because of the expansive soil is actually pretty wide in this area. So what you can see here, we have different colors basically representing different geology. Or when you're talking about the expansive soil, again, it really depends on the geology. From my experience, every time I was working on the geotechnical application and there was like a basaltic or basalt rock, straight away it was expensive. It's coming from the volcanic development. So in that case, it is straight away, I understand it is expensive. Whether it's high or whether it is intermediate, it's actually expensive. So this basically provides a good information or good hint where it's actually more volcanic or non-volcanic rocks. Now, these yellow and the red areas are actually the volcanic. So I can quickly understand here in this yellow and the red area, it's actually expensive clay. In these dark blue areas, it's more toward the high silt, and in this gray area, it's more toward the low silt. So it's still highly plastic. We got silt in low and high, but then it's not talking about the silt, we're not talking about the clay itself. This is a general overview of this labeling or the legends for the particular different sections. Now, that's one issue. It's the expensive clay itself. But then we got, because expensive clay or expensive soils are actually related to the water involvement. Now, we need to know the water level or the water depth, the groundwater depth in Victoria. So basically here, wherever it's red, it's basically less than 5 meters, all the way to green is more than 50 meters. So we already had this volcanic area, a volcanic rock in this area, and we already have the pretty low groundwater, less than 5 meters. So it's quite expensive. So it's quite susceptible to this swelling to happen during the different seasons of the year. In the green area, although the water is actually pretty low, like maybe more than less at 50 or more than 50 meters. However, we have here the high silt or high plasticity silt material. So again, it's not that. So in general, talking about this Victoria, we have this issue, expensive soil and that is one of the main reason we a lot of times see there's a lot of pavement rehabilitation happening. There's a lot of the construction renovation happening due to the cracking because the soil is not stable enough. It actually changes. So all this volume variation is actually causing these structure damages, and therefore. So this is some of the damages. Basically, when the clay is in its dry conditions, it's basically very strong, and when it's in wet, it becomes very soft. The structure actually sinks through the soil material. Some of the cracks development can happen within the mortar along the brick layering, but they are generally coming as a diagonal from the corner to the corner. The reason for that is because of the shear stresses that actually reduces, and all the shear stresses, all these cracks, the diagonal cracks, or the quite high angle cracks are actually from the shear stresses. So the first thing we need to know some of these identification of these particular clay, expensive clays. We have different type of testings to actually understand the parentic material or to understand the actual mineralogy of the clay. So we use the FTIR, the XRD, the SEM, or the TDA, DTA. That actually determines the type of the clay, the mineralogy of the clay. Some other ones we actually can do have a look at it, for example, from the experience when we see high pretty deep and wide cracks from the clay, so we know it's actually the shrinkage. So this soil is actually an expensive clay and so more. We also do some other testings regarding these criteria where we actually have these odometer to test. So basically, we try to find the swelling. What is the swelling range? What is this? Is whether this range? What's the swelling value? Whether the swelling value is actually within this particular range, and then you understand whether it's actually expensive or non-expensive. In some other cases, we have statistical testings. So it involves a range of the data, and then we do some statistical testing. We actually understand whether this clay is actually expensive or not. So this is the general idea of initially, if you want to prove scientifically this clay is actually an expensive clay. Some of the characteristics when you're actually working, some of the questions actually we work in the field identification that you actually work without any testing. When you're doing on site, you basically grab a sample of the clay and you actually check it. One of these characteristics is basically the expensive clays. It's basically it's sticky and it's quite difficult to be cleaned from the hand without any washing. Now, you might say all the clays are actually quite difficult to be washed, to be cleaned without washing. It's not all the times. So some clays you can actually grab it and you just rub your hand and then you can get it clean. Not 100%, but you can get it clean. But the expensive clays are actually very difficult. The other one is actually most of the cases, the color is dark black or gray, and it becomes shiny when you actually try to polish it with smooth object or smooth surfacing. They are actually very tough. They are really tough. It's very, sometimes you find it's like a rock, like a soft rock, quite difficult to actually break the piece of clay when they are absolutely dry. How do you know this? Sometimes you do this with the visual test. So this is the general field identification when you're working as an inspector to see what is the condition of the current condition of the site. Then we have this typical test to actually understand the according to the standard, what is the clay behavior. So we have this adiabatic test. Basically, we find the liquid limit, find the plastic limit, and then from the liquid limit and the plastic limit, we find the plasticity index. We have the direct shrinkage. Also, we have this free swell to understand the characteristics of the soil. That gives us a hint. Could be some calculation, some simple calculation, or some graphical identification, which actually provide us the expansiveness of this particular clay. So graphically, you actually in Strong Standard by using Strong Standard 1276 from 2017, we basically find the liquid limit, and then we calculate the plasticity index, and then we find which criteria or which classification is this particular clay. So if it's something with the CH, basically it's a highly reactive clay. If it's low, then it's low reactive. Also intermediate in this intermediate reactive clay. If it's low, then it's low reactive clay. So this actually provides us where we actually sitting at. We can see for the CHs or CHs, we're actually having pretty high liquid limit and a pretty high plasticity index. We can straight away see if we have a high plastic index, so it is actually a expensive soil. The asphalts, typically for the pavement design, pavement technology design, they have these kind of guideline where actually provides whether the liquid we have a liquid limit ranging from 50 to 70, and that's actually from low to high as expensiveness nature. The plasticity index numbers, and then even if you do some of the plasticity index multiplied by the SIF side, less than 425 micron, and then you have the swell as well, these ranges. So this gives us a hint whenever we're talking about the subgrade or the expensive clay in the subgrade, then we generally use this criteria to find which nature of expensive soil is actually it's sitting at. Now we're talking about the soil stabilization. So we already know, we so far understand the mechanisms of the soil, the limitations of how understanding the or evaluating the plasticity index and so on. Now it's actually the soil stabilization. Lime, Portland cement, fly ash, they have been used for quite long. I mean, fly ash at the moment is still in the stage of the research, but it has been actually implemented in the field. They have good characteristics in some cases, but for example, lime, the permeability for lime is it varies, not always have the constant whether it's high or low permeability. It actually varies. Portland cement can be quite expensive if you're actually having quite high expensive clay. Fly ash, again, in some cases works, in some cases it doesn't. Now, when we're actually talking about, and then you have the recycled glass, and then you have the recycled plastic. Talking about all of these different 5 additives for the soil stabilization. Now, cement is expensive, and including these all are actually environmentally not acceptable because actually contaminates the geology or the ground or the clay or the geotechnical application. It actually contaminates. So there are limitations in the environmental impact, and there are sometimes even for Portland cement, there are certain percentages that you cannot actually go beyond that because it's actually this is impacting the environmental issues. Now we have these limitations. However, when we're going to the enzymatic soil stabilization, enzyme itself is actually made from some plant resources. So it is biodegradable, but in a long term. At the same time, because it's coming from the plant and we're just getting from the plant and inputting back to the ground. So it's not environmentally, there's no issues at all. So some of the specific properties of this particular enzyme, it basically have the specific gravity of 1.1, boiling is about 100, the vapor and the evaporation same as water. The color is slight fermented, and the pH ranges from 4.4 to 4.8. So it's close to water, but not much. It's more toward the acidic. And the active enzyme is basically the amylase, oppase, and protease. So here, this particular enzyme, why is it good? Why is it used as an additive in the soil stabilization or the clay stabilization? We know the clay, the enzymes, sorry, the clay particles actually have negative charges, as we mentioned in the first couple of slides. They have negative charges, and all these positive or could be the water actually involves, and then making these different molecules put them together. However, enzyme itself is actually a positive. So there's a high electronegativity between the clay particles and the enzyme, which makes these 2 different items or objects get together pretty well. And it actually works as a protection which covers the clay particles from the water. So it's quite in-depth, but then we have done some macrostructural analysis, some laboratory tests to actually evaluate these different scenarios. So based on one of the laboratory tests, we tried to find some soil material, and then we initially evaluated the characteristics of this particular material, which is classified as a clay silt with a liquid limit of 23, plastic limit of 19.6, plastic index of 3.63, and the linear shrinkage as 7.68%. And this is the particle size distribution of that particular soil. Now, the different tests I actually took it were the quite deep macrostructural analysis using the macro CT. Initially, I did the unconfined compressive strength, which is known as UCS, and then the macrostructural analysis I used at the 15 micron resolution. So based on the output of these, I actually did some visual tests, the porosity content, the volume variation of the actual pores, what is their volume and what is their ranges, the shape of these pores, how do they actually change, and the different criteria of the shape, which is known as structural model structure model index. And then I also, once I knew the structural model index, then I went to the orientation, the angle of individual cracks within or individual void within the entire sample. So this is basically the UCS sample, putting in the MTS 1000, testing it for the UCS results. And this is basically a smaller version, 1 to 5, 1 to 0.08 of the actual sample of the UCS to be used for the X-ray testing. Now, in this case, oops, at the initial stages, we have to get the compaction. So with the soil compactions, basically, it's for the raw soil. We can see the moisture content is about 11.6, and then the dry density is about 2.02. But then by adding the enzyme, the moisture content actually reduced to almost 1.5, and the dry density is increased to 2.1. Now, the difference between for the moisture content of 2% when actually comes to the field work by reducing the water to be spread across the site at 2%, it actually reduces quite high expenses for the water content. At the same time, it's actually making the density higher. So the soil is actually becoming stronger. So, but only by using this particular enzyme material, we got two benefits: the cost of the material, the cost of the water, and the strength development. So from this graph, you can quite easily see the differences. Then, by using the enzyme and actual raw material, then I try to actually identify the moisture loss within the raw material and the moisture loss within the enzyme. So you can see the moisture as a gradient. The moisture is actually reducing much higher. The moisture is getting lost much higher gradient in compared to the enzyme material. Now the test I did actually, I did different elevated temperatures. So it was like 0. Basically, I froze the samples for the raw material and the enzyme material. And then I used the different samples. I used them at 15 degrees, 30 degrees, 45 degrees, and 60 degrees. And I did the entire test, including the unconfined compressive strength and including all of these microstructural analysis. Now I wanted to understand how the enzyme is actually behaving when it's experiencing the different temperatures, because we have different temperatures in Victoria. We want to see whether in high temperatures, in the low temperatures, what is the enzyme going to do, how it's going to, whether it's going to be improved or not. So I use this particular scenario of different temperatures. Then, based on the compressive and confined compressive strength and the different temperatures, we can see the enzyme is basically having a reduction compared to the raw material. But then, at the 15 or 30 degrees, is almost consistent as the raw material. At 45 and 60, slightly reduces. Now, a couple of issues is that could be because of the soil is actually not a consistent material, it's not non-homogeneous material, so it could be an issue there. However, even the strength is slightly reducing, but we got these cost saving of the water and the strength development. And we're gonna go through the next slides, the behavior of enzyme protecting the clay particles, which actually it's much more important by comparing it with this very small amount of the strength reduction. So by using the macro CT, the very first thing I try to actually get the sample to separate the void and to separate the solid, and then combine these two together and develop a 3D section. So here we can see the red dots or the red spots are actually the void, and then the green one or the light green one are actually the solid. This is for the raw soil, and this is for the enzymatic. And then you have the different temperatures going on from 0 to 60 degrees at 15 Celsius intervals. Now, for the 0 Celsius, we can see here, for the raw soil, we got void in a shape of the crack or in a rod-like. So it is lower porosity in this case, but then for the enzymatic is much higher. But we don't always want to have low porosity in the soil, because we, in some cases, we need to have these particular pores. Even though it's expensive on an expensive soil or clay, we need to have this void to be able to equilibrate the material behavior. So here we got for the raw material is actually low, for the enzyme is slightly higher. But then after by 15 degrees, the temperature for the the void for the enzymatic is actually increasing slightly. Relatively, it's also increasing for the raw material. And at this point, for 30 Celsius, now the void is actually starting again to increase for the raw, and then slightly increase for the enzymatic. And then for 45 degrees, you can see because of it's expensive material, the shrinkage is happening in this case. So there's a lot of void is actually happening within the raw material. However, for the enzymatic, it's still increasing, but not as much. It's much, much lower compared to the raw material. Now, this is the behavior of, even though during the wetting or during the low temperatures freezing, the void was quite low, was a bit higher compared to the control, but then at 45 degrees, it's actually controlling it. Now, the shrinkage is not much happening because the enzyme has actually protected this clay material. It's like provided a coating material for this clay material, which limits them from the shrinkage occurring. And if we actually go to 60 degrees, and 60 degrees is actually pretty high for soil. So we can see the void for the raw material is actually going pretty high, but then for the 60, it's almost remained the same. Now, this really, sometimes I can call it a smart additive, because it's actually controlling the material or the clay particles according to the temperature. At the low temperature, there is slightly high porosity because we need to do the expansions. At the high temperatures, there is still particular void content, again, to protect it from the shrinkage. So it's protecting it from the swelling and protecting it from the shrinkage, remaining the sample almost consistent throughout the different temperatures. So this is only some visual testing, but you can clearly see the differences. Then that scenario, when it came to the actual numerical for the porosity content, you can see here for the enzymatic compared to the raw soil is actually pretty hot, pretty low, but then at the temperature of 30 degrees, it just significantly increases at 45 degrees and then at 6 degrees. Compared to the enzymatic, it's still increasing for 45 degrees, but it's dropping again at 60 degrees significantly, even though for the raw soil it's actually happening. But then the differences or this residual between the two values is always significant between the raw and the enzymatic. Again, this numerically approves the use of the enzymatic is actually pretty good when it comes to the porosity content at the different elevated temperatures. Then here are some of the individual pore size. So this is for the control or the raw material, and this is for the enzymatic. So here we can see this is actually the particular volume size, and this is the frequency. So how many of these voids, this particular void size are actually there? It's for the every port within the entire sample. Then you can see here for the raw material, it's actually the frequency is actually going pretty high at different temperatures. And this is the same sample. It's the same sample that's happening, just experiencing different temperatures. For the enzymatic, it is still increasing, but it's at the same time, this increment is actually pretty similar. It's almost consistent. Again, it's controlling the behavior of the clay materials. Then here I did some of the sphericity variations. So when talking about the sphericity, basically a perfect sphere has a value of 1, and then it reduces. So something like this basically have 0.001. Depending. So these parameters are actually quietly used for the bond density in the biomedical engineering, and I use that parameters to be applied to the void within the soil or within the clay material. Here we can see the behavior of the sphericity of the void for the two different mixes. I've got the raw and then I've got the enzymatic. Now there is a quite good differences we cannot see from these particular graphs, but you can see the shape of the pores moving from 0 toward 0.7, 0.8 as the average. You can see the shape. Because this is quite difficult to actually analyze, because every dot here represents an individual pore within the sample. It's quite difficult to actually analyze, even statistically. So here, the best thing to be done, actually use the probability density function. So it's a density function. It's not actually the properties. That's why you got the more than 1 as a probability. And then this is for the raw material and this is for the enzymatic. So you can see here, the probability density is actually decreasing, and the shifting from 0. The shifting of the center of these curves are actually moving towards 0 as the temperature is increasing for the raw material, which really means the sphericity now, the spherical shape of the pores are becoming less spherical. And definitely when you have less spherical, we're not actually looking about something good. The more spherical, the better mechanical properties, because the perfect sphere basically means a perfect equilibrium forces. If there's a crack or if there's a pressure happening within the spherical, then because the spherical is perfect, the equilibrium forces will actually repel all these forces. But if something that is becoming less and less spherical, then there's a weakest point or the weakest stresses. So we're not looking for something like that. For the enzymatic compared to the raw, for the enzymatic, now we can see this variation is actually pretty constant at the same for different temperatures, clearly showing it's controlling the shape of the void to happen from moving from this spherical value of 0.7 or 0.75, for example, towards 0. So it's trying to control the shape of the void, which is really something we're looking for, because when the external forces are applied, there is almost the repelling forces quite good, which actually protects the structural behavior of the clay particles. I also moved all that kind of material, all that voids into different analysis. Now, structural model index is basically when we have a plate-like. So plate-like, we have just a crack. It has the XY values, but then there's also a Z. So it's a plate. It's a 3D crack. Route is basically the Z value is very, very low, but then X or Y are actually inversely related. So these are rod-like shape. And 4 basically means a perfect sphere. Again, these parameters are coming from the biomedical engineering, and when they try to test the human bone to understand what is the strength of this particular bone, they actually use these parameters. So now I used these parameters for the actual pores. We can see here for the raw material, the shape is actually the frequency is actually increasing at different temperatures. Again, they're ranging between rod to spherical. We don't have plate, pretty big cracks. But then for the enzymatic material, it's actually almost, the frequency is almost constant. And then it's slightly moving toward the 3.5, which is going toward the different, toward the spherical shape. But the actual frequency is almost constant. So we can see again from the different parameters or the shape variations, the enzyme is still actually controlling these voids or the actual clay particles properties. The final thing for the laboratory work here is actually using that structure model index and then finding the orientation of each of these voids within the entire sample. So every dot here represents a void, and there is a particular angle starting from 0 to 360 degrees, and then correspondingly to the actual structure model index, or whether it's going to be plate, whether it's going to be rod, or whether it's going to be a sphere. So initially we can see here for the raw material, it's low, and we have the for the enzymatic material is quite higher, but then the distribution itself is actually for the enzymatic material is the distribution actually is pretty high. Compared to the raw material, we got a thicker line compared to the enzymatic. So this thicker line represents basically there are some voids going from 2.5 or 2, which is having the shape of the rod to plate-like. Compared to the enzymatic, it's remaining almost over 3 to 2.5 to 3.5, which is rod or spherical shape. And that is actually for 0 degrees. Then when we have it for 15 degrees, this temperature is increasing. So you can see the void within the raw material is actually increasing as well. For the enzymatic, it's again remaining at almost at constant. And it's evenly distributed, which really means we have different shapes, different angles sitting within the sample. Then at 30 degrees, we can see these the pores, or the number of pores within the raw material, is increasing. But then for the enzyme, it's still constant. Now, again, it's controlling the actual pores. At at 45 degrees, the line is becoming thicker. And for this one, it's now for the enzyme, the amount of the pores are starting to become lesser. But then for the raw, it's actually increasing significantly, because we can see it's solid, in some cases, solid blue, which is full of voids compared to the enzymatic. Then at 60 degrees, you can see it's actually increasing even further. But for the for the raw material, but for the enzymatic, it's actually reducing. So this again really represents the control, the enzyme material. It's actually controlling the shape, the orientation, the porosity content, and the different shapes, such as structure index, model index of the void within the sample. So it's not only used as the strength development, but actually is also used as controlling the shape, because now this is what is really important. If we are able to have the shape of the void, or the shape of the particles, clay particles, to be controlled using some particular additives, because also once there's water involved, the shape will be changed. As I mentioned in my first slide, the shape of the clay, or the distribution of the clay particles, will actually be varied. By using something like with this enzyme material, it actually controls this variation, which is controlling the swelling, controlling the shrinkage, and then we having the structure stabilized or the structure is actually not experiencing these different mechanisms downward or upward. So we have a good understanding of this material in the laboratory scale, then moving to the field. So here, there was a work in Melbourne, the northern area of the Melbourne, which is consists of about 34,000 square meters. We have some of this statistical information or data, the annual rainfall in the area based on the Bureau of Meteorology. It's about 601 millimeters annually. The maximum temperature is about 20.8 Celsius as an average from 1991 to 2015. So we need to understand some background information of the environmental information, such as the temperature, such as rain, because they all coming to the shrinkage, to the swelling of this expansive clay material. So this is the location of the site, and this is the existing states of the site. We can see it's quite high fill. The clay is actually quite uneven, and it's different type of soil. But now we can see here is a black material, or the black soil, or gray, dark gray. So that really indicates this could be the expansive clay. So some of the tests were actually taken from the site, such as the different material for different boreholes. Then we got the different moisture content, some of them high, some of them are low. We got the liquid limit and the, excuse me, and the plasticity index, and then the CBR lab from the lab, and the swell. You can see swell 5 and 5.5. That's actually pretty high. Then by using the enzyme by itself as 1 to 312 ratio, which is every 1 ml of the enzyme is actually used for 312 ml of water dilution. And then for the cement one, we use actually 3% cement. Then we have the sample of the enzyme and the cement as well together to test it before going to the field. So we want to understand what is the enzyme for that particular soil material behavior, what is the behavior of the soil material using the cement, and then what is the combination of this material or the additives for that particular soil material from the field. The test here we took it is actually the unconfined compressive strength. It's a general test to understand the strength of the soil, the California bearing ratio, which is known as CBR, the X-ray diffraction, macro-CT tomography, and then we also did the field testing, which is the falling weight diffractometer. This is a very precise testing from the field, and it's quite expensive in general, but it actually provides a very good deflection throughout the entire site and very high levels. So by using these different four mixes, we have the raw, we have the enzyme, we have the cement, and then enzyme added with cement. You can see for the cement and the raw materials, actually, they're all about the different, but very small difference in the moisture content, and even for the dry density. But when we're using the enzyme itself, it's reducing the moisture content, and it's actually increasing the dry density quite high compared to the remaining of the mixes. You can see the impact of the enzyme in this case. Use of the unconfined compressive strength. We have the raw. The enzyme is slightly lower, but again, depending on the soil, because it's a non-homogeneous material, so we cannot really say this is the 100% effect. It's slightly lower, but it's only about 2-3 kPa. Cement, of course, when adding cement, it actually increases the strength significantly because of the properties of the cement. Then we have the enzyme and cement together. Now, the question here could be why enzyme is added to cement to reduce the strength, where the strength is actually pretty high. That is exactly right. However, when we're dealing with different environmental conditions, the protection of the enzyme, we obtain this information, this analysis, quite deep analysis from the laboratory. Now we need to protect our clay against different environmental conditions. So we use enzyme in that case. So again, we have the California bearing ratio. For the soil conditions, we can see at, for example, for the 5 millimeters, the enzyme itself has quite high CBR ratio compared to the raw. For the cement, again, it's going quite high, but then for the enzyme and cement together, it's light green, it's actually pretty high as well. It's comparably lower than for the cement, but again, the same scenario applies, the protection of the clay particles. Similarly, we had it for the non-sock conditions. The CBR is generally taken for the sock conditions. However, I wanted to know what is the scenario for the non-sock conditions, and I just wanted to know is there going to be any changes or not change at all? Seemingly, there's not much changes. I mean, there's significant variation as there is a slight variation for the raw and for the enzyme, but it's not significant. Now that why I wanted to know this because when you're talking about the expansive clay, they actually experience significant swelling when they are immersed in water, soft condition, and compared to non-soft. And that was my aim here to understand. Is there this significant when we using the additives, or there is not such significant? I clearly saw for the raw soil, it's actually doubled, but then for the remaining, it's almost remaining the same. So that was my idea to understand why the reason for the sock and non-sock conditions. Here, I did some the XRD or X-ray diffraction tests, and the reason I wanted to do that is I just wanted to find the crystallinity of the clay particles or the crystals. So for the raw, it's actually 57.1, but then when you're adding the enzyme and cement together, we can see the crystallinity is actually becoming about 64. So the bonding between the chemical bonding between the clay material or the clay molecules are actually becoming very strong, which is leading to develop this crystal size much stronger. So I wanted to understand what is the crystallinity of these by using different additives. We're not talking about much of these scenarios, but my aim here was just to understand this crystallinity. The macrosity using the porosity content only. Again, for the pores, for the raw material, the porosity is high compared to the enzyme. Actually, has reduced it. Cement is actually has increased the porosity again because of the cement and enzyme. The porosity also increasing. Now, the difference between the enzyme and cement, the porosity is actually increasing significantly, that particular residual. But comparing the enzyme cement with the cement only, it's not much. So here it's not much of the enzyme effect that's actually increasing the porosity, but actually the impact of the cement that is actually increasing the porosity. Then we did some of these field tests. So initially we stabilized the site at the first 200 millimeter thickness by using the enzyme and cement, and we did these weight falling diffractometer test at different spots. So they are about 10 meters away as a grid, and then we did some of the tests in this condition as well to understand what actually the behavior. Now in that case, this is the ground level, which is 0, and this is the deflection below the site. So you can see here in some spots, we have actually about 2000 micron deflection, and on some other sites, about 700, 800, or maybe the max, the minimum deflection we got actually here is about 400 microns. So this across the site. Again, having a site and quite about 34,000 square meters, and we're talking about microns of the deflection, we're looking about very precise information, very precise analysis across the entire site. So we saw some of these, and we have about 2,000 microns, and our aim was actually to go almost all of them across the site, less than 1.5 millimeter deflection. So again, we stabilize it another 200 millimeters of these in the area by using the enzyme and cement, and we did the testing again. Now we can see a much better variation. So the maximum here we've got is actually 1,000. So and the minimum we've got up to about 400. So we did hit our aim or the target. I think there were about only 2-3 locations across all of these locations, which we were about 1.6 millimeters, but the remaining were absolutely below 1.5. So just by using 400 millimeters thickness stabilization using enzyme and the cement, we actually hit the target of less than 1.5 millimeters, and we're talking about 34,000 meters squared. It's quite high, quite large. And I'll tell you what is built there then. So that was the conditions of the existing conditions. You can see this particular construction vehicle is almost stuck in the because of the clay behavior, and then after stabilization become nice and smooth. It looks like solid, and I did pass by a couple of times from this site, and they actually used crane on this in this area for the construction. So without the base, it was very strong. Now, why did they use it? So that was the initial, and now it's actually a bunning. So that site was actually used for a bunning construction. And bunning, we know it's industry. It's an industry building. So there's in some cases, in some locations, actually pretty high loadings. How they actually use the enzyme throughout the site, we basically use this particular equipment or the particular construction equipment. There's a tank, and it's actually connected to this enzyme or spreading machine. So you adjust the water to be incoming into this particular machine with the particular enzyme content, and it actually sprayed it equally or distribute through the entire site. Every location, every spot get the same content as required. Use of the other methods where they actually just spraying by use of the tank, for example, just mixing the enzyme with water and spraying, that does not actually distributes these additive equally throughout the entire site. So there are different instruments, different equipment used on site for perfect distribution of the additives, particularly when we're talking about the liquid additives. Another site is about 65,000 square meters with actually use of the enzyme as well. And we just located for in the southeast of the Melbourne for use of the white goods. Again, it was pretty nicely stabilized and just use of the enzyme and very low content of the cement. In geotechnical, I got several papers published, more toward the stabilization and toward the experience I've got as a geotechnical engineer. I have different type of geotechnical application undertaken. You can see this high column is basically the pavement design. So I like pavement, and I just wanted to use more toward the pavement. It was something that I actually was good at it, and I liked it. So yeah, and thank you very much for today.
Thank you so much for that presentation. Now we're going to open this up to questions. We already did have a question come in. I'm going to show a couple of slides that show the courses that we have related to this topic. But in the meantime, you can, if anyone has any questions, please put them in the Q&A. But Joshua did ask about 30 minutes ago, can the dynamic cone, don't even know the DCP or nuclear and soil grading or soil samples confirm that the soil type being tested in the field is expansive? And so that's in the Q&A if you want to reread that one.
I think I'll go through it again.
Okay, yes.
I'm just logging it. Okay, Joshua. Dynamic code DCP, nuclear and testing example, confirm the sort of test. The DCP is actually is widely used to understand the bearing. Density is actually used toward the nuclear density. Is actually used to compare the field density to the laboratory density. Now, with the nuclear density in Australia, according to AS, not I can't remember the standard name, but for the residential, you need to have 90%, 95%, above 95% for the residential of the nuclear test to the laboratory test. And then for the industry, you need to have at 98% plus. So it's not for the expansive soil. It actually just tells you what's the current density, and then you have to compare it to the laboratory density to approve the construction can be done. That's for the nuclear density. For dynamic compenetrometer, you actually use this to give you a quite good hint. So the DCP is number of blows per 100 millimeters, and then if you have a pretty high, then you can see this is actually soft, but that doesn't really mean it's expensive. It could be just even silt, even not. Could be a bit of a pretty high mixture of aggregates and clay, but because it's water there, so the DCP is actually with quite low number of the blows, it's actually going, it's hitting that 100 millimeters. So every 100 millimeters, you have to count how many these blows are actually counted. It's mainly used for the bearing, which actually gives you a good hint. What is the current bearing? But that current is a current bearing. It cannot be used as a bearing as the strength of the soil for the construction, because that changes. Maybe today is raining, next week is actually pretty hot, and that strength significantly changes. So really you cannot depend on the DCP itself for that purposes. But not much of the expensive soil. Again, expensive soil, we can actually test it is use of the laboratory test some of the quite high tech, such as SEM, X-ray diffraction, or geotechnical test, use of the atom that gives you a good hint. Swelling is one of the main, I mean, that's usually used to understand the expansive of the soil.
Um, so there's two more questions in the Q&A. I also just want to let everybody know, oh, another one just came in, that they can scan this QR code to gain access, gosh, to the certificate of attendance. This is only valid for 24 hours, so don't wait a long time to go do this. I also posted the link in both chats, the Q&A and the chat. In the meantime, there's, I think, 3 new questions here for you.
Okay, I can only see Joshua question. Trying to scroll
Okay.
down, I kind
So, QFI says, how is the enzyme harvested from trees?
oh yeah, how's enzyme harvested from trees? So this is something that I I I have always asked the supplier, and he's not able to actually share this information with me. So I don't have the enzyme myself. I don't actually produce this enzyme, but there's a supplier and he is actually producing it. He's actually the industry partner with me, but he never actually tells me how he actually produces it. Yeah, my apology. I really cannot actually answer this question because I don't know about this question. It's really something depending on the industry, his work.
Okay, and then there's something from Donovan. Do you see his questions?
Okay,
I think you have to, yeah, there you go. He's got 3 in there.
Okay. Right. So can you comment on the issue of sample homogeneity? It seems that the precipitation is concentrated at the sample start. Issue of sample, an issue of sample homogeneity. Okay, so for the homogeneity of the sample, we initially took the according to the Swan standard, we did the sieving, that particular sample, particular size sieving, whatever the size would be for that, and then we actually use that one. So now that is considered as a pure clay. The precipitation is contracted at the sample stop. Not necessarily, because the compaction has been happening. The moisture content, the optimal moisture content based on the dry density has been well mixed. So this optimal moisture content is not actually, because it's the optimal moisture, it's just sticking the samples together enough at that particular optimum. So there is no precipitation happening at different levels. It's not a liquid-like base. So there's not much precipitation happening, for example, in the concrete material. That, yes, that happens when you're doing the concrete, when you're doing the process of the compaction or the vibration. You can see in some cases there are aggregate actually going lower, and the cement product is actually going through the higher on the top of the sample. But in clay or in soil, because it's actually mixed very well, you make it homogenized, mixing homogenized, not the material homogenized. So there's no different precipitation happening in the different levels of the throughout the sample. Now, for question 2, which enzyme source do you use? Soybean, jack bean, etc. What is the absolute cost? Again, I don't know what exactly these enzyme sources are used, depending on the sources that the actual industry partner I have. The cost is not expensive, is comparably very cheap if you actually even compared with the cement material. So it's not that expensive at all. Question 3, it seems that the enzyme application is only limited to a certain temperature range. Have you considered the application in elevated and sunken temperatures? Okay. So we only went to the 60 degrees, from 0 to 60 degrees. The reason for that is I wanted to know the real application of the enzyme rather than the theoretical application. For example, if I use 100 degrees or Celsius, or for example, if I go, for example, -20 Celsius, there's not much application happening in this case. What I wanted to know, the worst case scenario here is happening 0 degrees. Sometimes you go to -5, but that's like freezing really cold, very rare. And even though you don't go much of the 60. But the reason I actually used 45 and 60, because the temperature that we experiencing above the ground level is not the same as the temperature the ground level is actually experiencing it. So I made it this top of typical ranges to have a good understanding of the behavior of the enzyme, because I'm using the enzyme for the field and I want to see what is going to be reaction in the field conditions.
Okay, so a couple more came in, one from Mark Daniel, probably you see that one, and then one more after that.
So you will post. Okay, so can enzymes significantly reduce the pI of soil? Significantly, it depending on when talking about the significantly pI. So you can't really use very low pI. If you have a pI, for example, of 40, 50, 60s, then that is even in the China standard, according to that table, it's actually not applicable. So there is different treatments that you need to use. Significantly using that, if you use, for example, in my case, I use 1 to 312 dilution ratio. there are cases they have used in different researches with the same enzyme. They've used 1 to 500, and some cases they have used 1 to 200. So it can really change the PI, but when you're talking about significantly reducing it, example, if you have a PI of 50 and you want to make it a PI of, for example, 10, 15, that's quite high. You need some additives such as cement to actually stabilize it for long term.
Did you see the one from Mark Daniel about the water ratio?
Yes, I'm reading now. So
Okay.
1 to 312 enzyme water ratio was indicated. What happened when this ratio is exceeded, say 1 to 300? Will it have significant effect on the performance? Yes, Mark, as I mentioned, different dilution, we basically have different behavior, different performance. In some cases, I think a colleague of mine, he used the same enzyme. He actually ran different tests, 100 and 1 to 100, 1 to 200, 1 to 3, 1 to 400, all the way to 1 to 500, pre high dilution. And he did find, with the same clay material, he did find there was actually variation. So here, why we used, so there was variation, definitely, for different variation. Now, for here at the 1 to 312, the question could be in your mind, you say, then why did you choose this typical number? This was actually taken from the average of the other studies. And then we finalized this could be a good, so we did some calculations, some statistical analysis, and we find this particular number is actually a good value to be used in this for this construction.
Okay, I'm going to give one more minute to ask any further questions. And if there are no more, we'll go ahead and end the webinar. Dr. Sadiq, thank you so much for your presentation today. It was wonderful. Again, I put the link for the certificate in the chat. If you need me to pull back up the QR code, mention it in the comments now, and I'll do that as well. Okay, I think that we are good, and thank you again, everyone. And if you want to see any future webinars, just visit where you did to sign up for this one. We always have webinars going on, and we love for you to attend. Thank you so much.
Thank you, everyone. Thanks for coming.